Example 1, a 1200 watt motor. What is that? Wattage. When you see watts, you know it's power. Motor lifts a 10 kilogram mass. $35 meters in 4 seconds. Does time matter?
Yes.
How efficient is this motor? See, in the industrial age, we didn't much care. They built things to last a long time. This goes right down to the appliances in your mom and dad's house, right? The old washing machine lasted 30 years, no problem. Nowadays, businesses make these things. They're designed to make money. You want it to last long enough so that people don't really get totally pissed off, okay? But you don't want it to last a really, really, really long time, because then people won't be in to buy a new one. So that's half the equation. But what people forget about too is the lighter you make something, the more efficient it can be, but okay, it doesn't last as long. So efficiency does come into play. All these old appliances, old fridges and stuff that lasted 30, 40 years, some of you guys still have them in the garage, they're energy suckers, right? They last a long time, but everything's big, heavy, inefficient. That's why it lasts, right? So that's the other side of the equation. The cheaper you make something, it could be more efficient. Okay, you can make something not cheap and efficient, but then it's really, really expensive. Most people don't want to pay that. So it's a fine line, right? Anyway, efficiency for a motor. Here's efficiency as a formula. And it should be kind of common sense, but sometimes the wording can make it a little tricky. It's power out over power in. So if something powers something with 100 watts, if you can get 100 watts out of it, useful energy, then that thing is impossible. Okay? Now don't think about the final question I had on my test in Physics 11, because I know there was something there. You're thinking about it, aren't you? Yeah, and I made a mistake, obviously, right? Okay, but it's impossible. Energy is never created, right? Energy is just conserved. It's just transformed from form to form. You can't have something give you more than what you put into it, okay? You can get some things pretty close. I don't have any concrete examples for you, but obviously the higher it is, closer to 100%, the better we all are off. So, power out, that is useful power, or useful, well, let's use the word power, not energy. Okay, power in means, like, that's what it sucks from the plug. That's the energy consumed. And not maybe just something we plug in, maybe it's you. How efficient are you? So when I say the machine, I might be talking about some carbon-based organism. Okay? That's the formula. So what do we know? We know power is work over time, and work is force times distance. So if we want to generate a new formula for those two, there it is. Power is Fd over T. That's not a force, that's a mass. So again, I could, well, let's do it. mgd over T. There's a new formula, right? Just combining three together. That's a force. G. D, that's a distance. T, that's a time. It's got to be meters, got to be seconds, got to be kilograms. If it's not, you got to convert it. And this thing is 857.5 watts. Okay? But this thing is consuming how much? 1200. So the efficiency, again, it has to be less than 100%, unless it's on your final test, in which case it could be above. All right? So power out, that's how much useful power I got from this thing. It sucks 1200. That's watts over watts. That cancels out, of course. And if you put that in your calculator and times it by 100%, it's 71% efficient. Okay? Sounds bad, but you know what? That's not bad. That's okay. You know your hot water tanks in your house? 60 to 70% efficient. Okay? They're not that great, because if you go stand by it, it's kind of warm. That means it's giving off heat. And the other problem is we always want that storage of hot water there in your house, right? So when you turn it on, it's hot. So even when you're not home using it, it fires it up, turns it off. Fires it up, turns it off. It wants to keep it at that nice hot temperature for when you get home. And they can't insulate this thing well enough so you can just fire it and have it sit there for a week and still come home and have like 70-degree water, right? Okay, they're not very efficient at all. Does anyone have the newer style of how you heat water in your house? You do? You do, really? Okay. I wasn't even going there. But instead of a hot water tank, you can have an on-demand heater. So it only heats, sorry? Yeah. It's just a big box that you put on the wall, and it has no storage of hot water. It just heats it as it comes in. But sometimes people buy it, it's kind of undersized, so if two people are trying to shower at the same time, well, you don't have hot water, because it can't heat it quick enough, right? But that's an on-demand hot water heater. Now, the reason why not everybody gets that thing, it's still gas-powered, is because it's about $2 to $3 grand. Hot water tank's only less than 1,000, right? Anyway, lots of ways you can do things, but it just costs you more money. And solar, yeah, if you want to do that to heat your hot water, great. But again, can you get it to how hot you want it for a shower? In the summer, but not in the winter, obviously. It doesn't matter how much sun's hitting that. All you're doing is kind of pre-warming it a little bit. And then you still got to heat it with something else, your hot water tank.
In the summer, we turn off the electricity for the hot water, and then it's just the stick.
Yeah. You know the worst part about that? Even if you don't use 1 cent of electricity, they still bill you $30-40 a month just for administration charges. Well, no, but there's like, even if you burn no gas, you still get a bill, right? It's a base charge. Just
to have it.
Yeah. Because, you know, let's call it another tax if you want. Okay. So efficiency questions, you got some of those. This one's a little different. What force is required to accelerate a 700 kilogram with driver F1 car from 0 to 100 kilometers an hour in 40 meters. Does that seem too short? Not if you watch F1, it's not. So what chapter are we in? Does that look kind of weird?
No.
It might. I can use kinematics to do this, okay? First of all, what do I want to do? Is that something I want for units?
No.
No. Yeah. Divide that by 3.6. First thing you should do, 27.8 meters per second. So, kinematics. I think I can solve this using kinematics, right? Oh, but wait a minute. I got forces. So, maybe it's a combination of kinematics and dynamics. what do I know here? I know that. It's asking for force. If I got a mass and acceleration, should work. Do I have a mass? Yeah. Do I have an acceleration? Not yet. Okay. What do I know? Blah, 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 blah. From 0 to, that's going to be VF. Do I got a time? I got a distance. I think that guy would work. To get my acceleration, 27.8 squared is nothing squared, and 2a times 40. Okay, so that squared divided by 80 should give us 9.7 meters a second squared. And then my force, it's directly proportional to mass and acceleration. And I get that's how much force is required. And I get that from their nice motors, of course. Anyone see the last Formula One? Oh, come on, you people. Don't you know how to live? So, in the old days, they would exactly design this engine to last one race. Okay? Because, again, the cheaper they make it, the more power you get. But it doesn't last as long. You want it to last exactly 2 hours, or 57 laps, or however long this GP is. At the last race, the guy blew up his motor 10 feet, well, actually about 100 feet before the finish line. Okay, but the problem is it's not the old days. And because of environmental concerns and keeping the costs down in the sport, because you can easily, Toyota spent $1 billion in F1 in 4 years, and they didn't even get a win. Yeah. So to keep the costs down for other teams, what they actually require them to use so many engines per year. That's the first way you can do it. The second way, well, again, what chapter are we doing? Energy. So there's this work energy theorem type formula that says that work is the change in kinetic energy. And what is work as a formula? Yeah, force times the distance. Do I have a force? No. But I have a distance. And what's the change in kinetic energy? 1/2 mvf squared minus 1/2 mvo squared. But my initial speed is 0. So FD is 1/2 mv squared. So F is 0.5 times m times 27.8 squared divided by d. And again, it looks the same, but it's just a different way of thinking about it. As a formula, it's a little more efficient because it's not in 2 steps. It's just like 1 step. And if you do that, of course, you get the same answer, actually a little off. Okay? But we're going to say that's the same as that. This guy? The VF? Oh, and I rounded that too? Yeah, okay. Yeah, all right. Round it twice and it's off by a little bit. But again, if this is what you're doing on the test, I'm going to mark it right? Okay? So, there's more than one way to do it. Day 3 on our sheet. And I am skipping certain questions, okay? So I recommend don't do them because they're more complicated than what they're worth. They might even confuse you. So it's not like up to question 40. I'm specifically eliminating a few of these questions. That should be enough to keep you busy for a few minutes.